This video is going to be going over how we use integration to solve work problems. Work meaning force times distance. So in physics, work is related to force, which is the push or the pull on an object. So when a force moves an object, we say the force does work on the object. In other words, work can be thought of as the amount of energy it takes to move the object. According to physics, when we have a constant force, then we can do force and distance and then take the product of that. In our English system here, the unit of force is the pound and the unit of distance is the foot. So we're going to say that work is in foot-pounds because it's the product of force and distance. In the metric system, we use kilograms and meters. So we say that it is a Newton that is the force needed to accelerate 1 kilogram of mass at the rate of 1 meter per second squared. So the common unit of work is Newton meter, also called a joule. And these are defined as kilograms per meter squared over second squared. So that is what a Newton is defined as. When we have a constant force, things are pretty easy. However, it is very rare for a force to be constant. So the work done to maybe compress or elongate a spring, for example, varies on how far the spring has already been compressed or stretched. So we're going to look at some spring motion in our first example here. Suppose we have a variable force, so not constant, that moves an object in a positive direction along the x-axis to A to point B. So you have some object here at x equals A, and there is a force that moves it to x equals B. To calculate the work done, then we might want to look at the subintervals over that time and how much work is done on each subinterval. We're then going to make those little subinterval partitions, and then we can add up that work done over time, where each little subinterval we then call delta x. You might see where we're going with this. So if you add up all of those work intervals, you end up getting the force on that itty bitty interval times that distance. Well, overall, as we let n go to infinity or the delta x piece goes to 0, this is what we're going to get. Again, let's look at springs and see how that works. So according to Hooke's law, the force required to compress or stretch a spring from its equilibrium point has some constant, and that depends on the physical characteristics of the spring itself. We call it the spring constant. So notice here, if the spring is compressed, we say that x is less than 0. And think about this like if that's a number line, right? That's x. So we're going to move it back to a negative x value. If you pull the spring out and then let it go, we're going to say that x is a positive value because your initial condition here is on the positive x side. So we can use this force equation in order to talk about how much work is done to compress or elongate the spring. So let's look at this first example here. Let's say that it takes a force of 10 newtons in the negative direction to compress a spring 0.2 meters from the equilibrium position. So you have this spring set up and it's just sitting there. And a force is then put on here. That force is 10 newtons and it pushes that spring so that it actually starts at a negative 0.2. How much work is then done if we want to stretch the spring the other direction? Okay, so let's go ahead and think about what we need to do here. The first thing we need to do is find out what the spring constant is. So remember, F is equal to K times X. So in this case, we'll have negative 10 because remember that force is going in the negative direction. is equal to K, and then the X displacement is negative 0.2. Well, if I divide both sides by negative 0.2, I get that my spring constant is 50. So F must be equal to 50x. So if I then want to stretch that spring, and I know I drew it from here, really it's from this point, 0.5 in the positive direction from equilibrium, then I need to be able to figure out the work done here. So that's going to be from 0 to 0.5, big F of x dx. So 50x dx. That's 25x squared from 0 to 0.5. And when I plug in 0.5, you could use a calculator for this. I get 6.25. And since we're in newtons and meters, remember that's going to have a unit of joules. This equation right here comes from my work equation right here. All right, here's another example. So what is the work done to lift a 20-gram child from the floor to a height of 2 meters? We're 1 kilogram, I think I said gram, sorry, 20 kilogram child. 1 kilogram is 9.8 newtons. Now remember, force is in newtons. So let's go ahead and convert 20 kilograms to newtons. So that's 196 newtons. And I basically want to know what is the work done to take 196 newtons and move it up 2 meters. So that's going to be the integral from 0 to 2 of our force, newtons, which we really don't need there, okay? And you can think of this in terms of dy if you want to, because I'm moving up and down. That's going to be 196 y from 0 to 2. And 196 times 2 gives me 392 joules.